Hi everyone, welcome back to the second lesson in lines and planes in three-dimensional space. In this video, we are going to focus on intersections, distance, and system. So here's what we are learning today. First, we will learn how a line intersects a plane. Secondly, we will learn how two planes intersect each other. Then we will learn how to find distance from a point to a plane. After that, we will learn how to find distance from a point to a line. And finally, we will talk about the consistent and inconsistent system by connecting algebra to geometry. So before we start, let's do a quick review. A line in parametric form looks like x equals x naught plus at, y equals y naught plus bt, z equals z naught plus zt. A plane in Cartesian form looks like ax plus by plus c, z plus d equals 0. So to find the intersection of a line and a plane, we substitute the lines x, y, and z into the plane's equation. So let's walk through an example. Suppose a line has a parametric equation x equal 1 plus t, y equal 2 plus 2t, z equal 3 minus t. And the plane equation is x minus y plus z equals 0. We substitute the line into the plane, which gives us an equation containing only t. Then we solve for t, plug it back to the line, and we get the intersection point. In this case, we get t equal 1. So intersection point is spelled 241. Oh no, 242. So this shows exactly where the lines parse the plane. So there are actually three possible outcomes when a line meets a plane. First, they can intersect at exactly one point. This is the most common case. Secondly, they might be parallel, so they never met. And third, the line might actually lie inside the plane, which means every point on the line satisfies the plane equation. So, intersection of two planes. Two planes can also intersect. To figure out how they intersect, we look at their normal vectors. If the normal vectors are parallel, which means one is a multiple of other, then planes are either parallel or exactly the same. If the normals are not parallel, the two planes intersect in a line. The direction of that lines comes from the cross product of the two normals. So we say the direction vector equals normal 1 cross normal 2. So, for example, take the planes x plus y plus z equals 3 and 2 minus y plus z equals 1. Their normal are spelled 1, 1, 1 and 2, negative 1, negative 2, negative 1, 1. These are clear, not parallel, so the planes must intersect in a line. We couple the cross product to get the line direction. Then we find a point on the both planes, usually be setting z to 0 and solving the two equation system. Together, the point and the direction vector gives us the complete intersection line. So, now let us talk about distance. The distance from a point to a plane is given by a formula. It looks like this when we read it: absolutely value of a times x naught plus b times y naught plus c times z naught plus d, or divided by the square root of a squared plus b squared plus c squared. This gives the shortest distance because it measures how far the point is in the direction of the plane's normal vector. So this photo clearly determines the distance. So for the distance from a point to a line, we use the cross product. If the line passes through point A and has direction vector v, and P is the point outside in the line, we from the vector AP, then we compute the magnitude of AP cross V and divided that by magnitude of V. This gives us the height of a parallelogram, which is exactly the perpendicular distance from the point to the line. So the systems of equation. Finally, let's connect everything to system of equation. A system of three equations in three variables represent three planes in a space. If the system has exactly one solution, the three planes meet a single point. If the system has infinitely many solutions, the planes share a line or overlap each other. If the system has no solution, the planes do not meet at a common point, usually because two planes are parallel or the arrangement doesn't allow a single intersection. So that's all for today. Thanks for your watching.